Now let's talk about Lagrange multipliers. As a reminder, this is the theorem. So suppose f from Rn to R and g from Rn to R are C1. So C1 means differentiable one time, and the derivative is continuous. So all first partials are continuous. And let S be all the x in Rn such that g of x is equal to C. This is the level set of G. And if x naught is a local extremum of f restricted to S, so f restricted to S means the same, basically is the same as f, but I restrict my input only to S. Then, if the gradient of g at x naught is non-zero, we have some lambda in R such that gradient of f at x naught is equal to lambda times the gradient of g. At x naught. So let's see how we can use this to solve problems. So consider f of xy equals f of x1 to xn, y1 to yn, where x and y live in Rn, to be x dot y, the dot product. And let me remind you what this dot product means. It means the sum from I equals 1 to n of xi, yi. And consider the constraints g of x equals the norm squared of x equals 1, and h of x, hy, the norm squared of y equals 1. So let's maximize subject to g equals 1 and h equals 1. So the first step is to compute all the gradients. So the gradient of f is equal to y1 all the way to yn, x1 all the way to xn. Because this thing is a huge sum, and if you take the partial, say with respect to xk, then you will just get yk. If you take the partial with respect to yk, then you will just get xk, hence this factor. And the gradient of g is equal to 2x1 all the way to 2xn and zeros in the bottom. Why? This is because x norm squared is x dot x. This is the sum of xi squared. And so if you take the partial with respect to xk, you get 2xk. And if you take the partial with respect to yk, you just get 0. And by the same reasoning, the gradient of h is zeros in the spot of the x's and 2y1 all the way to 2yn. And we want to set the gradient of f equals lambda times gradient g plus mu gradient h. So by this relation, I get that yi is 2 lambda xi and xi is 2 mu yi. But I also know that the sum of the xi squares is equal to the sum of the yi squares is 1. And so the sum of the xi squared, which is the norm of x, is equal to 1 is equal to 4 mu squared yi squared. And the norm squared of y is similarly equal to 1 equals the sum of 4 lambda squared xi squared. But I can take the 4 mu squared and 4 lambda squared out. So this is 4 mu squared times sum of y squared. This is 4 lambda squared sum xi squared. But I know these are also 1. These are also equal to 1. So it means that 4 lambda squared equals 4 mu squared is 1. And so lambda equals plus negative 1/2, and mu is also plus negative 1/2. Plugging in these numbers into here, I get that yi is plus negative xi for all I. Right? And therefore, f of xy is x dot y is, with these conditions, x dot plus minus x, this is plus minus x dot x, which is plus minus 1. And therefore, the max value must be 1. And notice that this gives a proof of the Cauchy-Schwarz inequality. Which states that for all x and y in Rn, the absolute value of x dot y is no larger than the norm of x times norm of y. So why does the above problem imply this? So notice that we showed that for unit vectors, the Cauchy-Schwarz equation is true. The Cauchy-Schwarz inequality is true. So this holds for, let's not use x and y, let's use u and v here. Because we maximized the dot product subject to the condition that u and v both had norm 1. And we know the max is 1, and therefore this dot product must not exceed 1 in absolute value. So I know Cauchy-Schwarz is true for unit vectors, but for arbitrary, xy, I can normalize them. I know that x over x norm and y over y norm are unit vectors. And so Cauchy-Schwarz hold. And so the absolute value of x over x norm dot y over y norm is no larger than 1. But this left-hand side, I can pull out the 1 over x norm and 1 over y norm because inner product is linear. This is equal to 1 over x norm, y norm, x dot y. And I know this is less than 1. And moving this to the other side basically gives me Cauchy-Schwarz.